Welcome everybody. This is our second webinar of this coming season. We hope to count on you among us in the next for the next webinars as well. Today, Dr. Nir Bar Gill will talk on the potential impact of the quantum technologies on our society, and he will describe how the diamond quantum technologies could contribute to fast computing and to medical diagnostic in the form of enhanced MRI. Our webinar will last for 45 minutes. You're now on mute, but you can ask questions anytime by writing them in the chat, and Nir will answer them. So please, Dr. Bar Gill, you can begin.
Thank you very much. Thank you very much, and thank you all for joining me today. It's my pleasure to be here. And I'd like to take this opportunity to tell you a little bit about my research, titled or focused on using diamond for quantum technologies. So basically, the plan I have for today is to tell you about the quantum revolution that's sort of happening now. And I'll tell you about it in the context of two different research directions or applications.
Sorry, we understand there are a few problems. לא שומעים אותי באותו כלום. אולי זה מפה? את יכולה לבדוק שומעים?
אפשר גם לכתוב להם אם הם שומעים.
כן. כן. Okay. Please.
Microphone is low.
אני בא איתך ואני הולך.
Hello everyone, can you hear me?
זה נראה שהם אמורים לשמוע.
Okay. Someone.
Please write something or let us know if you can hear me, just to be sure.
Okay. We understand that the problems are done, so I will begin from the beginning. Okay. So, welcome everybody. This is our second webinar of this coming season. We hope to count on you among us for the next webinars as well. Today, Dr. Nir Bar Gill will talk on the potential impact of the quantum technologies on our society, and he will describe how the diamond quantum technologies could contribute to fast computing and to medical diagnostic in form of enhanced MRI. Our webinar will last as usual 45 minutes. You're now on mute, but you can anytime ask questions by writing them in the chat, and Nir will answer them. So, Dr. Bar Gill, please, the floor is yours.
Thank you very much. It's a pleasure to be here with you today. And I'd like to take this opportunity to try to tell you a little bit about my research, focused on trying to use diamond for quantum technologies. And thank you all for joining. As Mara said, please feel free to try and ask questions during this webinar. So while we're talking, we're in the middle of a quantum revolution that I'll tell you about, how we're trying to harness quantum physics and the weird properties of quantum physics for various different actual real-life applications. And I'll tell you about two different directions we're working on. One is related to quantum computing, or using quantum physics to get faster computing. And the other aspect is trying to realize certain types of quantum technologies, and specifically sensors, such as in the context of MRI, which I will describe in detail a little bit later. So let me start with digital computing, which we all know and love, and even cats love them. And right now, while we're having this webinar, of course, we're all connected using our digital computers. And as you all know, that is a real revolution that's happened over the past several decades and has completely changed our lives. It all started actually quite a while ago, about almost 80 years ago, during the Second World War. And this was motivated by defense reasons, by actual military requirements. And specifically, one of the major milestones in the beginning of the digital computing era was the need to break the Nazi Enigma code. And you can see up here the Enigma machine. And the way this was done, and this was pioneered or led by the British, and specifically by this guy here, Alan Turing, who is one of the forefathers of digital computing, who together with his team built a computer. It's called the Bomba, who was specifically designed to break this Enigma code. And the idea of using a digital computer that was fast enough to try out different combinations that would allow them to solve this, this very intricate problem and gain some actual advantage in this war with the Nazis was a kind of a new concept. And of course, it was very successful, specifically in this context. But of course, much more than that. You can probably all tell that I guess Alan Turing couldn't imagine that the burning need of the 1940s would lead to the development of, I don't know, Facebook and Instagram and whatever, all the things that we're using today, and this Zoom webinar. And all of that is essentially encapsulated within the idea that in a digital computer, we can store the information in little tiny units of information that are called bits. And these bits are essentially, each bit is just a 0 or a 1. But if you string together many, many, many of those bits, you can basically encode any type of information, all the information in the world, essentially. And this is what we do in our digital computers. We have billions of bits running around within our computers and, of course, all around the internet. And that allows us to do all of these things that we're doing today. And it's, of course, extremely powerful. One example that I'd like to take while transitioning you from this digital computing revolution that's been happening already over the past several decades to the quantum computing revolution that's happening now is I'd like to describe what we all use today when we like to send secret messages. Now, all of you want to send secret messages now all the time. For example, when you're sending specific messages from one person to the other, when you're logging in through the internet onto your banking website or doing some online shopping, we'd like all of our communications to be secure. We don't want people to be eavesdropping and stealing our credit card information, for example. So all of us are using a specific type of encryption that's called RSA. RSA is just the acronym for the people who've invented this algorithm. The S is Adi Shamir, who's shown here, who's a computer scientist from the Weizmann Institute. And the reason we are all using this specific type of encryption is because it's unbreakable. Nobody knows how to break RSA. And actually, mathematically, there's no solution to this problem. So the only way to actually break RSA is to essentially try all the different options until we find the one that works. It's like looking for a password, and you have no way of smartly deciphering this password. You just have to try all the different combinations until you find the one that works. And you can imagine that if I can make this password an extremely long string of bits, and you sometimes see this when you connect to a secure website, you can see that they say this is secure with 128 bits of encryption, or I don't know, 256 or 1024, whatever. So you can already imagine that this is a really long number, and trying all the options for the longer strings would essentially take today's best supercomputer
more than the age of the universe to try and solve. So it's unbreakable. It's essentially unbreakable. We use it all the time. Also, governments and spies and everybody use it all the time. So it's a great encryption scheme. But if we would have the ability to use quantum physics, we would be able to break that. And for that, let me pause for a second and tell you what is quantum, or what is quantum physics. So I wouldn't try to really, within this limited time, tell you all the crazy stuff that go around behind the curtains of quantum physics. But let me just give you one example of the weirdness and also the strength of quantum physics. And that is kind of demonstrated in this little drawing here. And this is a very, very famous experiment that's been going around in the physics community for over 200 years. It's called the double slit experiment, because you have a little wall here with two slits in it. And sometimes this experiment is also called the young double slit experiment, because it was first demonstrated by Young in the late 18th century. And the idea is that, imagine that you have this wall with two slits in it, and we shoot balls to it, whatever kind of particle you like, balls, soccer balls, whatever you like. And you can imagine that maybe most of the balls just wouldn't hit any slit, just fall down. But some of them would pass through the left slit and then hit the wall behind them in this region here. And some of the balls will go through the right slit and hit the wall behind them in this region here. So you'd essentially see on the end wall, the end screen in the distance, you'll see two regions where balls would hit, two shades that basically correspond to the two slits in our wall. That is the classical system. That's what would happen normally. However,
Nir, there is one question. They're asking if that it's similar to X-ray.
The double slit experiment?
Yes.
So this double slit experiment, as I'll describe in a second, can be performed with nearly anything. It could be performed with certain types of waves, for example, electromagnetic waves like light or X-rays or radio waves, whatever one would like, but also could be performed with particles. And that's where the quantumness comes around. Young's original experiment was done with regular light waves, with visible light. And what actually Young showed is the picture on the left. He showed that if light impinges on this wall with two slits, then actually you don't get the image that we see on the right, you get the image we see on the left. You actually get two waves emanating from these two slits. These two waves interfere with each other in a very interesting way to form these lines, these periodic lines on the screen in the back, instead of these two shaded regions of what I explained before would happen with just classical particles or balls. So this experiment that was performed over 200 years ago by Young essentially demonstrated or proved that light was made out of waves. This was kind of surprising at the time, because the most famous physicist of all time, Isaac Newton, at that time decided that light was made of particles. And this result here of Young contradicts that result. It actually demonstrates that light is made out of waves. And it took a while for people to be convinced that actually Isaac Newton could be wrong. But he was, to some extent at least. He was never totally wrong. So this result here is what one would expect to see if the thing that we're shooting at the two slits is a wave. And that's fine. But what happened 100 years after Young and his original experiment is that Einstein came around and he said that you don't have to decide. Actually, light is both a wave and a particle in the weirdness that is called quantum physics. And even more so, not only light, but all the particles that we know are in some sense also waves. What that means is something that is completely counterintuitive. It means that if I now take a particle, this doesn't really work so well with big objects like the soccer balls or golf balls that I was describing before, but think about tiny particles, for example, electrons. If I would shoot electrons at this wall with the two slits, I would see the result that's shown here, the wave-like result. And that means that each and every electron that hits this wall will pass through both slits, will be at both of these positions at the same time, like a wave, and then will interfere with itself, with the chance of it being in each one of these slits to form the result that we see here. And in a nutshell, this is a very powerful and strange property of quantum physics. It's also very hard to understand, and if you find this to be kind of confusing, then it just means that you're okay. We all think it's confusing, and Feynman, who's one of the greatest physicists of the 20th century, actually said that if you think that you understand the double slit experiment, you don't really understand physics. So we don't really understand it, but we know that it works. We know that it works because this has been measured thousands of times with many different systems and many different particles, starting with electrons in the 1970s, and then going on to larger and larger particles, actually, demonstrating that this effect is very robust in the quantum world. It's hard to see it with our systems, but it is there in the quantum world. The important takeaway message from here is that a quantum system, a quantum particle, but generalizing a quantum system, can be in two positions, in two places, or in two states at the same time, as opposed to, you know, what we know from our own regular classical world. Unfortunately, we cannot be in two places at the same time. It doesn't work. In the quantum world, it does. How does that relate to the quantum computing revolution that I want to tell you about, and to this RSA encryption that we all use to shop online? Well, if a quantum system can be in two places or in two states at the same time, then instead of using bits to encode our information like we do in our regular digital computers, we could create in the quantum world something that's called quantum bits, or qubits for short. And these qubits could be both 0 and 1 at the same time, instead of having to choose, right? So take, for example, this little classical computer here that's trying to say 101. It's trying to say a little number using classical bits. But this bigger, stronger quantum computer, at the same time that it would take this classical computer to say 101, could actually say all the different combinations. It doesn't have to choose. So each bit is both 0 and 1. So it says 000 and 001 and 0 and 010 and so on, all of these combinations at the same time, because each one of the bits doesn't have to choose to be either 0 or 1. It can be both. And that is the essence of the strength of quantum computing, as opposed to regular classical computing that we have today. And this is something that I'd like to describe to you in a second, is something that we're trying to realize using diamonds in our lab. But let me just quickly relate this to the beginning of digital computing, or the digital computing revolution that happened back then, trying to break the Enigma code with Alan Turing. You remember the whole motivation for putting money and researching and trying to get digital computing to work was trying to break a code. They were trying to break the Nazi Enigma code. It was a very important goal. And today, we have this RSA code that all of us are using, and some people would like to be able to break it, some governments and some other entities, of course. And actually, in 1995, this nice person here, Peter Shor from MIT, he's a computer scientist, he wrote an algorithm that doesn't work because it requires a quantum computer. He didn't have one, but the algorithm showed that if he had a quantum computer, he could break RSA just like that.
So the strength of quantum computers is in a kind of in a nice analogy with the strength of digital computers 70 or 80 years ago, could, at least as a first interesting application, could be very interestingly applied to breaking codes. And that got a lot of government agencies and a lot of research agencies interested in trying to develop quantum computers and actually make that a reality. We're not there yet. Our codes and our online shopping are still safe, but people are working hard in trying to realize an actual quantum computer that could run Peter Shor's algorithm. And some of the companies and groups that are trying to do it, you might have heard of. So there's an actual quantum computer from a company that's less famous called D-Wave, excuse me. That's called D-Wave. It's an actual quantum computer that you can buy, costs a few $1 million. It's not very good, but you can buy it. And there's a few other companies that you might have heard of, like Google, IBM, and Microsoft, all are investing a lot of money in trying to actually build a useful and a better quantum computer. Maybe first to try and show that it can run Shor's algorithm and break RSA, but also for many different applications that right now we can sort of envision, but probably many more applications that we can't even imagine right now. I'll just mention a couple. If we had these super fast computers that could try a lot of different combinations much, much faster than any classical computer could do, we could calculate different deformations of molecules to try and design drugs that today we have no idea how to design and how to simulate them. Or maybe also to try to run artificial intelligence algorithms in a much faster way to allow us to incorporate them in a lot of real world problems. So these are just a couple of things that all of these companies are actually researching these days in conjunction with trying to really build a quantum computer. This is an interesting time now because what I'm saying is a little bit peeking into the future, but just as you can see in this publication from less than a month ago, Google has demonstrated using this is their quantum computer, it's called Sycamore. It has 53 qubits, quantum bits. Your little computer or cell phone has billions of bits, so it's a very small number. But still, this very small number of qubits has demonstrated something that's called quantum supremacy. They have shown that they can solve a problem. It's a very silly problem that's completely useless, but it's still a problem that they can solve much, much faster than the best supercomputer in the world. Much faster means in like 3 minutes compared to 10,000 years on the strongest supercomputer. So this is something that is called quantum supremacy, just showing or demonstrating that even today, with our limited quantum computer that Google has built, the quantum world is better, is much stronger than the regular classical digital computer. And this is just an early demonstration that probably in the next few years, 5 to 10 or something like that, we will actually see useful problems being solved by quantum computers that are way beyond the capability of anything that a classical computer can do. So let's say stay tuned for more news in the hopefully not so distant future in that area. But how does that relate to my research? I mean, I'm not Google, unfortunately. So my research is focused on diamond. And as you all know, there's this famous phrase, diamonds are a physicist's best friend. And we love diamonds, not because they're so nice and shiny and expensive. We don't like the fact that they're expensive, but because of the fact that they have very interesting properties. And I'll just mention that you all know diamond is made out of carbon. There are many things that are made out of carbon, like this piece of graphite that can be used as a pencil, for example. Both of these things are made out of graphite, but diamond is a very specific organization of, both of these things are made out of carbon, but diamond is a very specific organization of carbon atoms that give it nice properties, like the fact that it is transparent, it is the strongest material that we know, it is also the best heat conductor that we know. All of these properties come from the fact that the carbon atoms within the diamond are arranged in a very nice and special way. And this is actually the way they're organized. These little blue balls are supposed to depict carbon atoms, and this organization gives us the nice diamonds that we can use. we don't care so much about the strength or some of the other properties of diamond. We care about the fact that it can host specific types of defects. We actually care about diamonds that are not perfect. Now, no material in the world is perfect. Nothing is perfect. And every material, even if it's supposed to be made out of just carbon atoms, will always have something else in there, always. And for example, one could imagine this nice organization of carbon atoms, but at some point, a nitrogen atom, this N here, is replacing one of the carbon atoms. It's just sitting in its place. Why? Happens. And that's very common. It's extremely common. Another common type of defect is that another spot that is supposed to be occupied by a carbon atom, according to the structure of diamond, is just empty. It's a vacancy. That's why it's denoted by V. So this is also extremely common. These things happen. It even could happen that one of these nitrogens is sitting right next to a vacancy in the closest distance allowed by the diamond structure. That's also quite common. Actually, you might have heard of diamonds that have nice colors. For example, diamonds that are sort of pink. Pink diamonds have a lot of these combined defects with vacancy nearby. We actually call this defect with the very creative name, nitrogen vacancy, or NV for short. So this NV defect is common. It's not that rare at all, but we love this specific defect. And the reason we love this specific defect is because it has very interesting quantum properties. Let me tell you about it quickly. So first of all, one of the properties that this defect has is that it is like a magnetic charge. It has something that is called spin. It's kind of a weird property. It's also not rare at all. We all have spins in almost everywhere in our body, in pretty much anything. But this defect has a spin, and what's important about it is that it's quantum. I'll tell you what that means in a second. So we have this magnetic charge, this spin, in the NV that's sitting inside diamond. Now you can just think about it, if you want, as a little compass needle. So that's our magnetic charge. So we have a tiny compass needle sitting within the diamond. It's basically atomic size. It's like the size of the nitrogen atom and the vacancy nearby. And it responds to magnetic fields. It can point like a compass needle to the direction of the magnetic field. So that's all it is. So what does it mean that it is quantum? It means that you can think of a compass needle pointing in some direction, depending on the external magnetic field. But if you have a quantum compass needle, a quantum spin, like our defect, like our NV in diamond, then it doesn't have to choose whether to point, say, up or down. It can point both up and down at the same time. And that's the quantumness, the weird part of it. And that's how we, in our systems, in our lab, build quantum bits. That's how we build qubits. So our qubits are essentially these NVs within diamond. They're these quantum compass needles. And the zeros and ones are the compass needle pointing this way or the other. But instead of having to point one way or the other, it's pointing both ways at the same time. And that's the 0 and 1 at the same time. And that's how we can perform calculations using our defects in diamond. And just to give you a picture of where we're trying to take this, we're not there yet. This is kind of a sketch, an artist's conception of where we want to be. What we're trying to do is we're trying to take a piece of diamond with many different NVs in them, many different quantum spins or qubits, and connect them in such a way as to form a quantum processor. And this is something that we're currently working on. We don't have it yet, but this is part of a European funded project, one of an ERC starting grant that we've received to actually build a quantum processor, or more specifically, a quantum simulator. We want to use it to simulate and solve currently unsolvable quantum problems. So this is our take on creating quantum computing and quantum processors. And this time in diamond. Okay, so I hope I convinced you that quantum physics might be interesting for real world applications, maybe in the not so distant future by building fast computers, maybe even in diamond. But that's not all. We can also use our quantum compass needles, these NVs, for other things. And if I want to give you an example, where are we interested in measuring something magnetic in the same way that our NV defect in diamond is magnetic, is a little compass needle? One example that you probably are all familiar with is this MRI machine. An MRI machine is a wonderful medical diagnostic tool that basically what it does is measure spins, measure the compass needles that we have in our body. That's all it does. So it has this huge magnet in here and also little coils that are sensing the tiny magnetic fields that are coming from the spins in our body. They actually measure the spins in the water in our body. And it's an amazing tool that can do many different things. And today, MRI is essentially an irreplaceable medical diagnostic tool. We all know this. Still, it has its limitations. One of its big limitations is its limited sensitivity. It's not sensitive enough to measure many things. And it's an interesting thing to try to think of why this is so insensitive. One of the major reasons for this is the fact that all the spins in our body are just random. They're oriented in each and every way in space. They're not pointing in a specific direction. And now when our MRI machine is trying to measure them, it's looking at the whole area in our body with lots and lots of different spins pointing whichever way. And the total field that comes out of it is close to zero because they point in opposite directions and it all sums up to zero. So that makes our sensitivity very, very small. That's also the reason why we use a huge magnet here to try and make them point a little bit in a specific direction. And that limits, for example, our ability to do early diagnosis of certain types of diseases, which had we had that capability, that would have been an extremely useful tool. So one way to try and use our system, our NVs in diamond, to fight this problem and to help MRI is through something that's called hyperpolarization. We have very good control of our NVs in diamond. We know how to point them in a specific direction very, very easily. We just have to shine some green light on them and they all arrange themselves like soldiers. So we know how to point them in a specific direction. So what we could do, what we could try to build, is something that we call a polarizer, where we take some contrast agent, some chemical substance, and run it very close to our diamond in such a way that we transfer the polarization, we transfer the direction that the NVs are pointing into those spins of this contrast agent. At first, they're completely random. They're pointing in random directions. But after they interact with our NVs, they will be pointing in a specific direction. They will be ordered. And if they're ordered, then the signal that the MRI machine would get from them would be much, much larger. So imagine a situation where we take this type of solution, this type of substance, we pass it through our diamond polarizer, through the system, and then inject that contrast agent into a person, into a patient that goes through an MRI scan. And that would allow us to map the flow of this contrast agent within the person with unprecedented sensitivity. And this is something that could have a huge impact on medical diagnosis and early diagnosis of certain types of diseases, specifically heart-related diseases and cancer. This is something that we're currently working on as part of a large European consortium that's called Metabolics. It is funded by the EU Quantum Flagship Project, a huge funding scheme of the European Union that's designed to promote research and actual applications of quantum technologies. And these are the members of this consortium. And actually, we're also part of another European project that's part of their Future and Emerging Technologies funding scheme. That's more of a basic science project that's related to the same ideas. It's called Pathos. also a large European consortium that we're part of. So there's, we're not there yet. We have very preliminary demos that are working, but not to the extent that we actually need. But on the scale of a few years, 2 to 3 years, we're expected to be able to demonstrate useful hyperpolarization, useful polarization of a relevant contrast agent using NVs and diamond. So this is one demo of how NVs and quantum physics could in the near future contribute to useful quantum applications. Maybe very quickly, I'll mention before I sum up, I'll mention an actual MRI type sensor that's built around our NVs. And for that, let me show you just quickly a little animation of how we measure magnetic fields using our NVs. This time we don't want to polarize something and send it into an MRI machine. We want to replace the MRI machine completely. So say that we want to measure magnetic fields with our NVs, with our diamond. So our NVs are pointing in some direction. As I told you before, we can just shine green light on them and make them point in a specific direction that we want. We can then use microwaves, not this microwave oven, but something more complicated, to rotate these spins in space very controllably. And we can do it in such a way as to make them super sensitive to external magnetic fields. An external magnetic field will make them rotate. And this rotation, we can then, using a combination of microwave fields and light, we can then measure. And maybe one of the highlights of this is that we can measure this magnetic signal, this direction of the NV spin using light. We can measure it just using light. And that led us to think about whether we can make a magnetic sensor or an MRI sensor that is at the end of an optical fiber. So we would like to try and build a handheld MRI device, or maybe even an endoscopic MRI device. So something that's just sitting at the tip of an optical fiber with a tiny diamond at the end. And then we could use it to measure magnetic fields. And these magnetic fields could be these magnetic fields that are coming from the spins in our body, could be an MRI signal. And even though this could never replace a full MRI machine, it could allow us to come close to a point of interest, to maybe some suspicious region in our body that a doctor would like to examine, and to measure it with very, very high sensitivity and very high resolution. Just because of the fact that we can just extract all of the information optically through this fiber. So this is currently a project that we're working on. This is a first demo where you can actually see an optical fiber. The whole fiber is going down here. And at the end, there's a little diamond sitting on top. The green light is this light that we use to point the NVs in our diamond and to get them to sense magnetic fields. And without going into any details, these plots here demonstrate magnetic sensing using this device for both constant and oscillating magnetic fields, which are relevant for MRI type measurements. So again, we're not there yet. This is an ongoing project, but this is just an early demo of how one could utilize the quantum and optical properties of these NVs and diamond for interesting quantum applications. So to summarize, I hope I convinced you that the quantum revolution is here and now. It's happening. We're living in exciting times. I think that on the longer term, 5, 10, 15 years, we might expect to see actual quantum computing coming around and having significant impact on useful problems. So far, they haven't done it, but the progress is impressive and could be very useful. And maybe on the shorter term, as I was showing you a few minutes ago, quantum technologies, broadly speaking, including various types of sensors, hyperpolarizers, MRI, and so on, could actually result in significant improvements of what we have today as part of these European consortia and projects, and of course, many other experiments and research that's going on around the world. So I hope that you've enjoyed this presentation, and I thank you for your attention, and I'd be happy to address any questions that you might have.
Thank you very much, Nir, and we're waiting for your questions. Okay, so saying thank you very much, everybody, and you can ask any question by raising your hand, or we have Natalia. She's asking, your research is geared towards helping diagnostic versus healing?
I'm sorry, I don't understand. What does it mean? Oh, versus healing. It's. I don't think that it's versus. I think that right now the capabilities that we're pursuing in the context of quantum technologies and quantum sensing are technologies that could most directly influence and enhance diagnostics. Healing or other treatments and therapeutics are beyond currently the applications that we know of us being relevant for. But for various state-of-the-art sensors, as for example MRI that I mentioned in my presentation, we believe that we could have a significant impact in the aspect of diagnostics, and maybe even importantly early diagnosis, which would allow direct healing and treatments that, of course, would not be relevant if early diagnosis is not possible. So this is currently the direction we're focused on.
Okay, and Mr. Kluger, he's asking, how do you think the position of the Hebrew University versus other university in the world and in terms of quantum technologies?
I think that the Hebrew University is very strongly positioned in the context of quantum technologies and quantum science in general. The Hebrew University has the oldest quantum information science center in Israel and one of the older ones in the world. It's been established, I think, in 2010, if I'm not mistaken. And of course, currently it's also the largest in Israel. It is it builds a very strong collaboration between many researchers in the Hebrew University that are addressing quantum physics and quantum technologies from various different directions. And just as an example, some of the work that I've presented is done in collaboration with Alex Retzker, who's a theorist that works at our department. And he's also one of the founders of a startup company that's called Envision, which is part of the consortia that's working on this MRI hyperpolarization project that I mentioned before, this metabolics. So I think that currently the Hebrew University is well positioned. I would also strongly stress that it's not enough. I think we can do a lot more. And I think with your support and maybe the support of many other people, we would like to push forward and to bring ourselves to the level where we have the personnel and the resources to really be not just at the forefront, but maybe first. And we're currently impacting various types of research directions around the world, as exemplified by these consortia that we're partnered in, but we would like to do more. And I think that we are in a position to break additional barriers and be at the forefront of this very, very interesting, these very interesting developments.
Okay, we have two questions. Challenge is asking, who are your main competitors in terms of university in the world, and who are the most advanced university in the fields? And then we'll have another last question.
So this is a very important question. The field of the specific field that I'm focused in, which is studying these quantum applications and properties of these defects in diamond, of these NVs, is a field that's quickly growing. It's a relatively young field that's been around for about 15 years, but it is growing. Currently, the world leaders that we are competing against are a strong group of researchers at Harvard University in the United States, and a very strong group of researchers that's in Germany, in a region that's centered around Stuttgart, Ulm, and Mainz. they are, in a sense, our competitors, but also our collaborators. So we want to be at the forefront of this field and others, and we are, in a friendly, scientific way, competing with them, but we're also collaborating with them, for example, through some of these European projects and through others.
We have another question from Mr. Ben Cohen. What is the cost of using diamond versus a very strong magnetic field to align the spins?
That's a very interesting question. The bottom line answer is that even though diamond is expensive, it is a much, much cheaper solution. Let me explain. First of all, I didn't mention this during my presentation, but all of the diamonds that we use are synthetic. They are real diamonds, but they are not natural. They're not mined from the bottom of the earth. They're grown in lab. That makes them very good diamonds, much better than the natural ones that are being mined. But also, it makes them cheaper. Still pretty expensive, but cheaper. The other important point to note is that the MRI system, the large magnetic fields, or other schemes that people have designed and even demonstrated for doing similar type of hyperpolarization, require huge magnetic fields and also usually very cold temperatures, and that ends up requiring a huge building that is much, much more expensive than these diamond samples that are, centimeter size. So I hope this, even though it's kind of quick, I hope this gives you a flavor of how, even though diamond in itself is an expensive material, it ends up being orders of magnitude cheaper than the technology that's required not using these quantum systems.
We have, in this regards, another question. How easy is today to manufacture a diamond to your requirements?
So, as I mentioned, our diamonds are synthetic. They are manufactured in lab. Doing that is not so easy, yet not so hard. So it requires a level of expertise that can be learned or trained, and it requires the right type of equipment. And for example, all of our research and demonstrations and projects that we're running are done in collaboration with companies that grow diamond and sell diamond, usually with very high quality. And for example, one of these companies is sitting in England. It's called Element 6. And they are also part of some of these projects that I mentioned, allowing us to move forward with very high quality diamond and very high quality NVs within this diamond. Maybe I'll also mention that we're also collaborating with an Israeli company called ICDAT that also grows diamond with very high quality. So this is something that requires know-how, requires equipment, but can be done rather straightforward.
Okay, thank you very much.
Thank you.
I think it was very, very interesting, and I will send to all of you the recording of the webinar in the next few days. And thank you again, Dr. Bar Gill.
Thank you very much.
Thank you.
Yeah.